Hey there, my name is Alejandro, and welcome back for day 107 of me doing the NeetCode 150 challenge. So today we're doing another NeetCode Medium 2D dynamic programming problem, and without further ado, let's get straight into it. Okay, today we get NeetCode Medium problem 494, target sum. Seems like we've solved this problem before, and there's something in here, so let's make sure that we clear that. When do we submit this? We submit this December 25, 2024, so Christmas Day. Was this the NeetCode Daily on Christmas Day? Could have been. Okay, let's read the problem. You're given an integer array nums and an integer target. You want to build an expression out of nums by adding one of the symbols, plus and minus before each integer in nums, and then concatenating all the integers. For example, if nums equals 2, 1, you can add a plus before 2 and a minus before 1. Concatenate them to build the expression plus 2 minus 1. Return the number of different expressions that you can build, which evaluates the target. Okay, I was going to say, oh, wait. No, okay, these all count as unique. I was like, okay, if you have like, 3 plus 1s and 2 minus 1s, is that the same combination? No, the order does matter. Okay, I was about to, I was going to get scared a little bit because I remember in, I think the problem was partition equals subset sum instead of the NeetCode 150 here. Over here at some point, like, I took a long time on this problem, and at one point I was thinking of, like, essentially adding a plus or minus sign to each number, so that way if I ever reach 0 at the end, I know that I partitioned it equally. But the problem was essentially like summing things up and so on at the same time and keeping it one-dimensional. Here we have two benefits on our side. The first one is that we can make this a 2D dynamic programming problem because, it's under the 2D dynamic programming section, so we have a lot more flexibility in the way that we write our solution. And secondly, it seems like they want the number of different expressions. They don't want, like, some evaluation of a specific expression to see if it reaches 0 and so on. So gonna be very, very, very convenient compared to that. So the hardest part of dynamic programming is always coming up with how to write the recurrence relations. So here we gotta think. So the point is that we'll have two cases at every single number, right? We'll either add a plus sign or a minus sign. So what I'm thinking is that we probably need an index for each index inside of nums, right? Because for each index, we want to give ourselves the flexibility of choosing the case where we add a minus sign and a plus sign, right? But we must evaluate the target. So I'm going to guess that we have a target thing at the end. So that way, when I is greater or equal to the length of nums, we can make sure that to see if we hit our original target or not. And we can initially pass in a value of target, and then at the very end, only consider the solution true if it ends up being 0. So, okay, so it seems like it is exactly like the problem that I was doing in partition equals subset sum, but this time we have the added flexibility that essentially I can make this a 2D dynamic programming problem. I guess these problems are very, very, very much so related, except this one is about different number of ways, not if it's possible. So, okay, so in this problem, I'm going to guess 2DDP is needed just because it's about number of ways, not whether is it possible to reach target. Okay, so let's just get this right away. It seems very evident to me already that what we're going to need is an index I and a current target. So here, for now, we'll keep it simple and only consider a finish case when I is greater or equal to the length of nums, right? Not when target is less than or equal to 0 and so on. Well, first of all, if target is less than 0, we know we can return 0, right? Because target must be greater or equal to 0. Now, if I is greater or equal to the length of, and now, yeah, self.nums, here we'll say return target is equal to 0. Okay, so here we'll have self.nums and self.memo is equal to nums, comma, memo. And here we'll return self.dp from index 0 with an initial target. And here we'll say, if I, comma, target is inside of our self.memo, we will return self.memo of I and target. Very excellent. Here this is base case 1, so yeah, so if you reach the end of the numbers, you want to make sure that you hit a target of 0, because essentially we're going to add this target over here. Well, I guess you want to go from 0 to target, right? So if anything, we can do self.target just to make our life very, very, very easy here. Yeah, I'll take this out. So nums target memo will be nums target and an empty dictionary. And then here we can just do 0. And here instead we can do self.target, right? So that way it makes it very clear. We don't have to think about minus sign, plus sign, so on, blah, 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 right? Because otherwise it would be subtract if you choose not to add a number, so on. Let's just keep it this way. That way we make this problem absolutely as easy as possible for us. And then when we want to change the O of 1 stuff at the end, we can absolutely do so. Okay, so base case, made a choice every single digit in nums, so return 1 indicates it is a possible, it is expression if and only if the built up target is equal to the original target. Here we can even say current sum. The current sum is equal to the original target. Otherwise, return 0, as it is not a valid expression. There you go. Now, the numbers are not plus or minus, so actually something like this is actually useless. Okay, well, because we can make things negative, positive, and so on. So now we don't ever have to worry about overshooting target, because now you can go negative and essentially reach target another way. So essentially, this should be our base case, but also probably our only base case. Makes sense. Okay, here what we're gonna do is we'll say, well, no, not a for loop. Let's think. So I have an I and a current sum. So here we'll say current sum, just to make things a little bit simpler. So case 1 is going to be add a plus in front of num. So here we'll have num is equal to self.nums at index I. So if we choose to add a plus, then case 1 will be the number of permutation combination valid expressions possible from index I plus 1 onwards, where we fixated the choice for index I to be a plus sign. So here we'll do current sum plus the number. Case 2 will be add a minus sign in front of number. So here case 2, again, same thing, we move on to index I plus 1 because we fixated the decision for index I to be subtracting the number. There we go. And again, this will return 1 at the end of each case if it is valid or not. So the result here is simply res is equal to case 1 plus case 2, self.memo of I, curse sum will be equal to that result, and we return that result, and there we go, bada bing, bada boom. I expect something like this to be nice and working. Very much so. Accepted. Let's submit. And there we go. We have a working solution. 183 ms beats 37.58%. Absolutely excellent. So as always, I think what I'm going to do is I'm going to try to challenge myself and write this as a bottom-up dynamic programming solution. So here we'll do exactly that. So we want essentially, here we'll say our DP array is equal to, well, things can be way beyond target though, is the problem. Well, are all the numbers positive inside of nums? They are indeed. So max target sum nums is equal to sum of nums. Max target equals sum nums. Min target is equal to negative sum nums. Target range equals max target minus min target. So here we'll say DP of zero, target range. Here we gotta be careful, right? Something like this, plus 1 for this in range length of nums. Now, all the ones where here we should do length of nums plus 1. So here I shall also say n is equal to length of nums. let's make this absolutely clear. Target range. There we go. So in all the cases where sum is equal to self.target, so dp of n, right, we always do this and so on, and target is equal to 1. Nice. Okay. Now we'll say for I in range from n minus 1, negative 1, negative 1, for sum in range ooh, yeah, this is gonna be interesting. Doing this bottom up might actually be kind of difficult here. This is not one specific direction, so maybe this is one of those where you build it up. Ooh, that's gonna be tough. That's going to be pretty tough. Otherwise, is our solution efficient enough? I guess we're at 37.58. Yeah, doing this bottom up is going to be a little bit challenging. Sum minus num, sum plus num. Very interesting. Because yeah, now we can't necessarily go from one direction to the other because we might need one direction's values before we reach one. So essentially it's like you kind of start from the middle. Maybe you do for I in range sum of nums, sum is equal to 0. For offset in range sum of nums, left sum is equal to sum is equal to negative offsets. Right sum is equal to offset. Yeah, it might be a little bit tricky here. Yeah, it might be a little bit tricky. Here we'll start with 0. L sum, R sum, L sum, R sum equals 0, 0. Minus equal to 1, R sum plus equal to 1. L sum or actually, does it even matter at this point? Alright. Can I just loop over all of them just because I'm going to do index I plus 1 always, right? If I'm always doing index I plus 1 for an index I, it actually doesn't matter, right? here what I'm thinking then is I just do for sum in range, you know, min target to max target plus 1. We'll do dp of I, sum. I equals 0. Nums at index I plus num less than max target val plus or equal to I plus 1 sum plus num. Oh, the indices might be a bit weird. Maybe I do plus some nums. Oh, this is going to be interesting. Maybe I do something, yeah. In range, target range. Yeah. Yeah, this is very interesting, right? Because we have an array of indices. Index 0 really represents negative whatever. Some nums. Yeah, this is interesting. We just have to figure out how to do this correctly. Yeah, the problem is that I have target range many indices, but really I want index 0 to map to negative sums. Makes it a little bit hard to think about. Not gonna be the end of the world though. Sum to index. Some nums. Def index to sum index minus some nums. So maybe we do something like this. New sum equals sum plus num. If sum to index of new sum less or equal to dp of I new sum index is equal to this. dp of I you will say curse sum index sum to index of curse sum. And here we should do the same thing. So it'll be minus num. Right? And here return dp of 0, 0. Wrong. Ooh. Sum to index of 0 maybe. That did not work. That did not work at all. Probably because this should be sum to index targets. Okay, so that works. Let's submit. Does not work. Well, that's not really possible. Oh. Use test case here. I see. So if it's out of the target range, first of all, yeah. If it is not the case that, you know, min target less or equal target less or equal to max target, return 0. Okay, so that case is fine. Okay, although that actually made our solution a lot slower. Really? Okay, makes sense. I mean, we're looping over every single possible target every single time, doing a lot of nonsensical work. Okay, so this is the first time that my bottom-up solution is actually slower than my top-down one. It makes sense. Don't start visiting sums that you don't have to. Here we do plus num, and here we do minus num. Does that still work? Does. Yeah, but it barely reduces any work. I understand. It's slow. Okay. Not a worry in the world. We'll get rid of our bottom-up solution just because it's slower than the top-down one. And the top-down is just by far easier to understand anyways. But at least, you know, we gave a bottom-up approach a shot, which is all I care about because it gives me extra practice with writing bottom-up dynamic programming algorithms. But yeah, so we have a 186 ms runtime solution, beats 35.29%. I'm sure that, you know, this is probably people that found a better way of writing the bottom-up, but I don't want to make this video unnecessarily lengthy for no reason. At least we gave it a shot. We found a working way to do it bottom up. That makes me happy. I'm just getting more experience with it, and one day I'll get to the point where not only can I write them bottom up, but I can also write them bottom up and efficiently. So, right, figure out a correct topological ordering where I don't have to go through unnecessary edge cases and so on, which is just the case here. Like, you know, obviously, if I don't have to look at every single sum, then I probably shouldn't, and so on, etc., 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 right? And that is kind of the idea. But anyways, as always, in all my videos, I do a quick recap if I was able to solve the problem. So for this one, essentially, this problem just asks the number of different expressions that you can build. So what is a valid expression? Well, you're given an integer array nums and a target. And for every single number in nums, you can either put a plus sign in front of that number, or you can put a minus sign in front of that number. And you want essentially to after you put the plus or minus sign for every single number in nums, you want to ask yourself, okay, if I take the sum of all those numbers, positive or negative based off your decision, does this sum up the target? And if so, that is a valid expression. Otherwise, it is an invalid expression. You want to count the total number of valid expressions you could build in the end. And so, no better man for the job than my good old friend dynamic programming. And so here I set up my self.num, self.target, self.memo, classically nums target as our input, and an empty hash map where we'll store our results for memorization. And here we'll do self.dp of 0, 0. So what does this mean? Well, I have a dynamic programming function here that essentially says, okay, we'll find you the number of valid expressions starting from index I in nums so in nums from index I onwards, and we'll always have a current sum that we start playing with, right? At the very beginning, I want essentially the number of valid expressions from nums at index 0 onwards, so for all the numbers. And at the very beginning, we haven't chosen to put a plus sign or minus sign in front of any number and so on. We actively have a current sum of 0, right? So that's why I pass in 0 for the current sum, right? Obviously, if we've seen a result before, we'll return that result. Otherwise, here's the very first base case. I'm going to make a decision for every single number in nums. I'm either going to add a plus sign or a minus sign, and at the very end, I'm going to check if it equals my target, right? The sum of all those numbers. So what I'm going to do is, okay, my only base case is going to be once I is greater or equal to the length of self.nums, because that means I've essentially I've made a decision of plus or minus for every single number in nums. Now, once I've made a single decision for every single number in nums, again, I'll always return my current sum. So once I've made that decision, at the end, I want to return, okay, was I able to reach the original target? So I return 1 if the current sum that we have after having made a decision for every number is equal to the original target. If it's not equal to the original target, it is not a valid expression. Otherwise, it is indeed a valid expression. So here I either return true or false based on whether or not it's a valid expression. It's valid if and only if it's the sum that was built using these decisions actually adds up to the original target. And obviously in Python, if you try to add true or false, the values will be 1 and 0 respectively. So it's just a very, very convenient side effect. So this is, you can think of it as me wrapping this inside of an int, or it's essentially I'm treating the trues as a 1 and the falses as a 0. I do that pretty typically in my videos. Okay, otherwise, what we're gonna say is okay, if we're not at the very end, I greater or equal to length of self.nums, we're not at the very end, we still have some decision to make for some of the indices, right? So we'll say, okay, we'll grab the number at index I. And for the number at index I, we have two possible decisions. Either we put a plus sign in front of it, or we put a minus sign in front of it, right? It's one or the other. If we choose to add a plus sign in front of it, okay, we lock in that decision, right? For index I, we've locked in the decision. So then we need to look at the decision from index I plus 1 onwards, right? Remember, dp of I is from an index I onwards inside of nums. If we choose to put a plus sign at index I, then we've locked in the decision for index I, and then we only care about the potential decisions that we make from index I plus 1 onwards, right? So if we choose to lock in as a plus, good, we can go from index I plus 1 onwards. But we've locked, to make sure that we essentially denote that we locked in our decision, we'll take, hey, whatever our current sum is, we'll add number to it, because we're choosing to put a plus sign in front of the number. Remember, all the numbers in here are non-negative. So when I put a plus sign in front of it, it'll be the positive version, right? So here I'll choose to add the number to that set of current sum. I locked in the decision of putting a plus sign at index I. Otherwise, my second and only case will be to add a negative sign instead in front of the number. So again, I lock in the decision for index I, so I can move on to index I plus 1 onwards. And to essentially show that I locked in the decision, I take the current sum and I subtract number. Again, they're all non-negative, so by subtracting the number, I essentially effectively put a negative sign in front of the number, right? So that way, it's I modify the current sum based off whether I put a plus sign or a minus sign. So at every single index I can either add a plus sign or I can add a minus sign. And so I compute the number of valid expressions where I lock in a plus sign at index I, as well as the number of valid expressions where I choose to lock in a minus sign at index I. The total number of valid expressions from our current index I and our current sum will be the sum of these two values, right? There's only two possible cases, add a plus sign or a minus sign. So compute the number of cases when I choose to put a plus sign, compute the number of cases when I choose to put a minus sign, and add those together. So again, this is the number of cases when I choose to put a plus sign at index I. This is the number of cases when I choose valid expression, sorry, when I choose to add a negative sign at index I. So my result will be the sum of those two counts of valid expressions. I'll make sure to cache that result in case it's ever needed later on. So at index I incur sum, which was our original input, we'll cache the result as the result we just computed it, and then return the result. Bada bing, bada boom. That's essentially how it's able to solve this problem. So again, it's literally like go through every single index I, and you have two possible cases. Either you put a plus sign or you put a minus sign, right? That's kind of the idea. And every single time you do so, you keep track of a current sum, and obviously you add the number or subtract the number based on the decision you made, and so on, and just cache the result so that you never do more than this many subproblems and however much time per subproblem. So like without caching, essentially what I'm trying to say is I would probably time limit exceed it, because you'll end up doing a lot of the subproblems again, right? For example, with 1 and 1, we can either do -1 and then +1, and then we have essentially a current sum of 0 and 3 more ones, and then we go from index I. But we could also have done +1 and then -1, right? And so for both of these, we'll end up with the case where we have a current sum of 0 and the index I is equal to 2, right? So we've just visited the same subproblem twice, right? So it's going to be a lot of repeated work. So by caching the results this way, you end up saving on all that repeated work and make a solution that is actually possible. Here, as always, we'll just make sure that we denote whatever the time complexity is. So in this case, we have O of so here, there's n possible cases. So this is every single possible index I inside of nums. So here we'll have n, so where n is equal to length of nums times all the possible current sums, right? So this will be times target range. Target range negative sum of nums, range from negative sum of nums plus 1. Length of this. So essentially, in terms of Python notation, essentially, I have a current sum, right? How many possible current sums can I have? Well, it's going to be, whatever is the minimum possible sum I can get from the numbers in nums, which is essentially choosing to put a negative sign in front of every single number. So it'll be take the sum of nums and multiply by -1, right? Because essentially I take every single number in nums, slap a negative sign, and that ends up being the minimum possible value I can get, right? Otherwise, it's the reverse case is I put a plus sign inside of every single num in nums, so I can have, up to some nums total current sum. And so my range of sums lies from, this minimum possible value that we can have and this maximum possible value that we can have, right? If all the numbers are ones, for example, then we can get a lot of examples and so on. So in the very, 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 very worst case, we actually do end up filling this range. It'll probably not be the case in a lot of times, but technically in terms of worst case complexity, what we're trying to achieve is what is worst case. So worst case, it is the full range from the negative sum of nums all the way up to the sum of nums and so on. So it's essentially 2 times the sum of nums. So of times sum of nums, since target range equals 2 times sum of nums. Nice. Okay. Implies n times s subproblems where n equals length of nums, s equals sum of nums. And then the type per subproblem here, so okay, time per subproblem. So this is O of 1, O of 1, O of 1, recurrence relations are always of 1, of 1, of 1. Okay. So of 1 time per subproblem implies of n times some s total time equals okay, there we go. So the total runtime complexity of this is okay. So yeah, that's the total time complexity. So the total time complexity is equal to O of the length of nums times the sum of nums, right? That's kind of the point. Yeah, so essentially it's like O of n times s total subproblems, right? Because like, curse sum can they can arrange like, negative sum of nums all the way up to sum of nums, which is equal to 2 times sum of nums total possible sums. But again, O of 2 times something is just O of that something. Like O of 2n is like O of n. So it's like essentially this becomes O of n times 2s. So we get rid of the 2, so it's O of n times s. And so we have like, length of nums times sum of nums total subproblems. O of 1 time per subproblem gives us an O of n times s total runtime complexity in the worst case, where n is equal to the length of nums and s is equal to the sum of nums. So hopefully that clarifies the time complexity right there. And yeah, okay. So as always, otherwise, let's make sure that we come here and check off the fact that we did the problem. So very nice. We're now almost done with the LeetCode mediums in the 2D dynamic programming topic section. We only have 2 more LeetCode mediums to do, so that feels absolutely nice and fantastic. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate it if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, my friend. Bye-bye.